This will be the laboratory 4, thin layer chromatography, which is found in FOX 2.2. I would be surprised if you hadn't had some laboratory experience in this, as they do thin layer chromatography in many chemistry courses and also typically in biology courses as well. So some of this may be a little bit familiar to you. We're going to use amino acids. And as a reminder, the amino acids are the building blocks of proteins. And amino groups and acid groups make up most of the molecule, and then they have what's called an R group. Okay. Amino acids then have the same structure, except each one has a different R group. As a reminder, there are 20 naturally occurring amino acids within a protein. Okay, so again, they have the amino group, the carboxyl group, remember that's an acid, a central carbon, and then what they often call the side chain, the R group, the rest of the molecule, whatever you want to call it. So here are examples of the different 20 amino acids that we naturally have put into proteins. And so you can see some are nonpolar, right? Some are polar, and some are polar and electrically charged, some are acidic, some are basic. You don't have to memorize these or their structures or anything. I just want you to know there's different types. And it's the side chain, shown in yellow, green, blue, or red, that really dictate how the amino acid behaves in a solution. So what we're going to do is we would set up a plate. Now this is a TLC plate, thin layer chromatography plate. You can use paper. This actually is a glass plate that has a silica gel on it. And what you do is you draw a little line that's a reference, and you draw that in pencil because pencil is insoluble in the solvent. So as the solvent moves up, it's going to move the amino acids, but we want to keep that reference line, right? And you want to make sure that reference line is above where the solvent is. The solvent doesn't have to be 95% ethanol. It could be, 50% ethanol, 50% acetone. There's a lot of different things that it could be in it. Typically in lab, we would use 50% water, 50% methanol. Okay, so and it really matters what the solvent is, because the solvent will dictate how far each amino acid moves. And that's because each amino acid has their own R group, which gives it distinct properties. And if you change the solvent, you change the properties of each amino acid. And it really depends to a large extent about how well it dissolves within the solvent. So once you draw the line and know where it's going to be in the solvent, you have to spot the plate. Typically in lab, we would use, different amino acids. As an example, we'd use alanine, aspartic acid, histidine, lysine, and methionine. Then number 6 would be some unknown amino acid. And the idea would be, by knowing what the behavior of the first 5 were, then we could compare it to the behavior of the unknown and figure out what that was. Right? So once we spotted the plate, and the way you do that is you just use a pipette, a micropipette actually probably works better. Just put a little dot right where you want it, right on this line, and do it all the way across, stick in the solvent. And what happens is the solvent moves up the paper, or in this case, the silica gel on the glass plate. And as it moves up, what it does is it drags the amino acid behind it. And the more soluble the amino acid is, the farther it's going to move. And so what you do is you watch the solvent move up the plate, and when it gets up to a certain level, then you go ahead and pull it out, draw a line where the top of the solvent was, and then measure between the line you spotted and the line of the solvent, and then figure out how far each spot moved. So it's not a very difficult experiment from that that standpoint. Then what we have to do is, because of the way the experiment works, we cannot see the amino acids on the plate. They're actually invisible. So the first thing we have to do is we have to dry the plate. And the reason why you don't do that is you don't want the spots running. Then we spray the plate with a substance called ninhydrin. And ninhydrin, what it does is it intercalates into the amino acids, and it allows you to basically see it. So it sort of sucks in the amino acid, and wherever there's the amino acid, you'll be able to see it, and it'll appear on the plate. We often use the incubator to dry it again, just because it makes the spots appear faster. Then we would measure, like I said, the distance of what's called the front. Okay, so you measure from this line to this line, right? So you see this arrow here. That's called the DF. You measure the distance from the spotting line to the middle of the spot. That's the DS. And you divide DS over DF, and you get your what's called RF. A couple things about RF. It doesn't matter if you use centimeters, millimeters, inches, whatever, right? The units are going to cancel each other out. So RF is a unitless value. And kind of note this. Let's look at the extremes. If the spot did not move off the line, what would the measurement be? Well, let's see. We want to measure how far the spot moved. If it did move off the line, the movement would be 0. So 0, whatever the DF number was, right, would be 0. So you can have theoretically RF values that are as low as 0. What would happen if it moved perfectly with the solvent? Well, then it would be exactly right on the edge of the solvent, and the distance you measure would be the exact same as the distance the solvent moved. So again, the distance divided by the same distance is going to give us 1. All right, so in rare circumstances, we could have a 0. In virtually no circumstance would we have a perfect 1.0. And in all other circumstances, it's going to be a number between 0 and 1. So it's going to be point something. And that's a good thing to remember in your head. If you don't get point something for an RF value, it's likely you did it wrong. Okay? So there's not much else to that experiment in terms of explaining it. You can use other substance, like in biology, they'll often use the chlorophyll pigments, things like that. In chemistry, you can use a lot of different chemicals. You can do thin layer chromatography with anything that's soluble in a solvent. So there's nothing magic about it. And since it was such a short introduction in terms of things, let's kind of look at the discussion and keep going with the same idea. So we've already seen this, and we've already seen the amino acids, right? We're not looking at a protein, we're looking at individual amino acids, and we're looking at usually 5 or 6 different kinds. And again, each amino acid has their very own R group, which gives it very distinct chemical properties. Okay, so some of the side chains are non-polar, some are polar. Again, some are polar acidic, some are polar basic, and some are polar without a charge. Okay. Also, if you look at the different structures here, right, some are very simple. So like the side chain of an H for glycine, right, simplest one. Alanine just has a methyl group on it, pretty simple. But we come over here for tryptophan, we see this double ring, very complicated structure. Remember, each corner of these rings, unless it's identified like the N here in tryptophan, is a carbon, right? So you have some very complicated molecules that have a much higher molecular weight. Some fairly simple molecules are going to have a much lower molecular weight. So the size in this case differs as well. And typically the ones, that we do in lab, we do, some of these oftentimes We often do a hydrophilic one, a polar one for cysteine, and we are doing aspartic acid usually, or maybe lysine. So we have a number of different amino acids that you could do for this experiment. And basically, it's nice to use ones with different properties. You don't want all like small ones that are polar, right? You want to look at some different properties and try to get them to separate, So uh, we would use, again, this is going to become important in a few minutes, a 50% water, 50% ethanol mixture. That's the solvent. It's going to move up the plate, right? So what we typically do is, let's say we use alanine. Okay, so we'll go back here and say, okay, where's alanine? Well, it's right here. It's a non-polar one, right? It's pretty small. Aspartic acid. So come over here and go aspartic acid. Oh, look, that's in the polar ones. That's actually an acidic, negatively charged one. We use histidine. So as you come back over and you look at histidine, you'll see that's also a charged one, but it's a positively charged one, so that's also polar. We use methionine. When you use methionine, you'll see it's a larger non-polar one. All right, so by looking at the different ones, we can see that we have a number of different amino acids with fairly basically different properties. All right, and then again, once you let them spot, it usually takes a couple hours, minimum an hour and a half. You can probably go a lot longer. You never want the solvent front to reach the end of the plate, and as long as it was somewhere far enough where you could expect separations from the different spots, and it didn't reach the top, you'd be fine in terms of that. And usually in laboratory situations, about an hour and a half, up to 3 hours. And then you'll do your calculations with the measurements. So first of all, let's kind of think about what's going to cause our amino acids to move. Well, if the amino acid spot was totally insoluble in the solvent, it will stay right where it was, right? But if it was soluble, it would move with the solvent. And the more soluble the amino acid is, the farther up the solvent it will move, okay? So something you probably learned in chemistry and you've heard before is this basic idea of like things tend to dissolve in like things. And since that is true, polar amino acids tend to move further in polar solvents because they're more soluble. Likewise, you go the other way and say, oh, non-polar amino acids tend to move farther in non-polar solvents because they dissolve better. And it's the properties of each that allow it to have typically a fairly unique distance it travels within the solution. And then we can use those unique distances to identify the unknowns. Okay. So our plate, like I said, is a silica gel. And what happens is it grabs amino acids and kind of holds them back and tends to slow the migration. Okay. In addition, since these plates are sitting straight up, basically up and down in a solution, they've got a little bit of an angle because we lean them against the side of the chamber they're in. But for the most part, it's moving up against gravity. And as the molecules move against gravity, gravity slows them down a little bit. And so the larger the molecule, the greater effect gravity would have on it, so they would move slower. So for our purposes, we're going to worry about kind of two things. Solubility, how soluble is the amino acid in the solution, in the solvent, right? And that, to a large extent, is determined by polarity. Nonpolar things tend to be more soluble in nonpolar solutions, and polar amino acids tend to be more soluble in polar solutions. In addition, the molecular weight. The larger the molecule, the heavier it is, the slower it's going to move. right? So smaller molecules will move quicker on average. So when we look at the theoretical value of the RF values, do amino acids theoretically have different RF values? The answer is yes, but sometimes it's hard to tell experimentally because they're very similar. And so once we figure out an RF for an amino acid in a particular solvent, that RF is not going to change for the most part. Maybe temperature or other things might affect it a little, but that RF is going to be that RF every time. It's not going to be, histidine in a polar solvent is not going to be, an RF of 0.43 one day, and then the exact same experiment be 0.78 the next. It's going to be consistent every day. So as long as the solvent and the plate are the same, then the RF will not change. Okay. Now, the longer you go, the better separation you have, but it's still proportional to how fast the solvent front is moving. So if you only let them go for 5 minutes, let's say, then most of, or maybe all of the spots haven't moved enough for you to be able to differentiate between which one's which. But if you let them go for 2 hours, now that the front's moved, almost all the way up the plate, let's say, then it's going to be a lot easier to figure out what amino acid is the unknown. So one of the things that's nice about our experiment is the ability to see not just the movement of the molecule, but we can also, on the glass plates especially, look at not only the color, but also the shape. And I like this one. This is not exactly what our experiment necessarily looks like. And usually we have multiple unknowns here, and oftentimes we use amino acids that don't move. So this is not our plate, but it is a plate of some amino acids in a solvent. Okay, and so I like this one because it's nicely colored. So you can see this amino acid and that amino acid are different, and they're different for a bunch of reasons. Okay, one, if you measure the RF, and you can kind of see down here, here's our starting point, right? This pencil line here. Here's our finishing point, our pencil line here. So if we measured from this pencil line to that pencil line, we would get our DF, right? That's the solvent front. So that's our DF. That's this one right here. So the point is you can measure different RFs, and sometimes they come out the same. And again, just kind of, it's hard to draw these exactly, but we'll go straight down, or at least try to with the mouse. We'll start at the line and go up to the middle of the spot. So that's one of them. We'll use this color for the other one. We'll start at the middle, try to go straight down. And you'll notice these have about the same middle part, right? So the DS for these are going to be very similar, if not exactly the same. The DF will be exactly the same because the lines are parallel, so that will be there. So we might get the exact same RF for amino acid 4, and let's say this is the unknown, right? And based on the numbers, you go, oh, it's the same amino acid, right? But if you take a look, right, notice this one's red, this one's purple. It's not the same amino acid. So sometimes the RFs come out similar looking, even though they're distinctly different amino acids. When that happens and you can't differentiate between them, what's often a good way to kind of make them move differentially is to use a different solvent and do the experiment again. And since they have different properties because of their different R groups, they will likely move at different speeds and have different RFs this time when you do another experiment. All right, so that's kind of what we're looking at for the RFs. And let me kind of look at a little bit of specific data and kind of see how that would work. All right. Okay, so here's the sample data in the lab supplement, and you can look at a couple things, but let's calculate this first RF. Okay, so for the first RF, we know the DS, right, because we measured that from the original line to the middle of the spot was 1.3 centimeters, and then the DF was 11.8 centimeters for all these. Okay, so to figure out the first RF, we take the DS over the DF. So I just punch in 1.3 into a calculator, divided by 11.8, and that's going to equal 0.11. So this is going to look bad, but we'll go ahead and do it. It's going to equal 0.11. That's because 1.3 divided by 11.8, the centimeters cancel out, and I'm left with 0.11. So that's my RF. Now, I didn't have any other numbers here to calculate, so I want to know aspartic acid. And you just keep on doing this. So aspartic acid would be 1.9, and then you divide by the DF, the distance of travel, it's still 11.8, and that's going to give me 0.16. So for this one, I'm going to get 0.16. And you just keep on going down and figure out those numbers. Now, when you get down towards the end here, in our unknowns, we actually put 2 amino acids in our unknowns. And we did that for a couple of reasons. One, it's an example of how you can purify a solution by using thin layer chromatography. And back in the early days of chemistry, that's how we purified solutions, was often using TLC. We don't do that anymore. We use more industrial techniques. We can do it faster, cheaper, in greater volumes, something like, what they call HPLC, high pressure liquid chromatography. But it's a technique to separate different things dissolved in a solution, as well as figure out unknowns. So if you went through and you did all this, let's skip down to this unknown B. So unknown B has 2 spots, one that was measured at 1.9 and one that was measured at 11.8, right? So just kind of, look at what I'm talking about, right? So let's say that you had a plate that looked like this, right? And again, I'm trying to draw with the mouse, so it's not going to work. So here's my original spotting plate. Here's the where the solvent front was. And then you would have an amino acid, let's say right here. That was right here. Okay, so that's where the spot is. And in this case of the unknowns, let's say this was a plate for the 2 unknowns, maybe you end up with a spot that looks like that and a spot that looks like that. So we have 2 spots within a solution, and that's because we took 2 unknowns and put them in. So the first one, right, would be measured at 1.8, let's say, sorry, 1.9. So this will be the first one. That'll be that one. And the second spot, 8.5, would be that one, right? So again, the DF we saw was 11.8. So from here to here, right, that's 11.8. That's the DF. And then the DS would be 1.9, and this DS would be 8.5. So when we went back and did this calculation, this RF would be 0.16. And what we notice is, hey, look, that matches this. And so it's likely that since the RF of this one matched perfectly the RF of that one, that this unknown is aspartic acid. Okay? The nice thing about this data is you look, it's really hard to confuse one number for another, because notice, the numbers 1.3, 1.9, 4.6, 5.5, 8.6, 7.1. So they're really pretty distinctly different from each other. And so without even calculating the RF, you go, oh, this is 5.6, it's going to be that one, right? So those are going to match. And this is 1.9, and those are going to match, right? This is 7.2, and those are going to match. This is 8.5, and those are going to match. So you're not going to get exactly the same RF, but you'll get them pretty close. And so you could say, well, I understand how we can say the unknown B, the first one, is aspartic acid, but how can we say, this one? So if you calculate the RF for valine, you get 7.1 divided by 11.8, and that's going to give you 0.60. Now, if you do the unknown, you're going to get 7.2 divided by 11.8. And since it moved farther, it's going to be 6.1. Right? So even though they don't have exactly the same RFs, if this is 0.61, this is going to be significantly higher. That's the next closest. The 5.5 is going to be significantly lower. So it's the only one that matches. And so you're not going to always have the exact same RF value, but you will have an RF value that is going to be close. All right. If we wanted to kind of make this data kind of reverse, then you can go ahead and switch the solvent. And if we have a different solvent, we're going to cause all of these DS's to move differentially based on it. And so, another way to look at it more general is, let's say that, let's go back to this experiment. We have these two results, right? So these are two amino acids, right? We'll call the bottom one A and the top one B. All right, and we know one of them is polar. So we're going to say one of these amino acids, A or B, are polar. Okay, so we have our solvent on the bottom, right? So here's our solvent down here. Okay. Do you think that solvent is polar or nonpolar in this solution, in this experiment here? And you say, okay, well, how do I tell? And the way you can tell is look at this and go, okay, look, this is a polar solvent, right? And B moved much further than A. Okay? Now, size makes a difference, but probably not this big a difference. And let's even make it even cleaner and say, okay, we know these are the exact same size amino acids. But we know one's polar, one's nonpolar. Which one's the polar one? Well, if we said this was a polar solvent, so I'm going to put a P here for polar, right? Then amino acids that are polar will dissolve better in a polar solvent, which means they will move further. So the B would be the polar one, because it moved the farthest in the polar solvent. And the A would be the nonpolar one, because it didn't move as far. All right. Now, what's interesting is if we switch this to a nonpolar solvent, those results are probably going to flip-flop. Okay. Those results are kind of flip-flop. Another way to look at this is, let's kind of look at it again. So we're going to do another plate. We're going to say, all right, here's our two lines. We're going to draw in our solvent. So here's our solvent down here on the bottom. And we're going to say this solvent is nonpolar. All right, so the solvent's going to be NP for nonpolar. And let's say that both amino acids are also nonpolar. But we get a situation where One moves here. And the other one moves here. All right. We know these are both nonpolar, yet one moved farther than the other. How to explain that? Well, they're both fairly soluble because we've got nonpolar and nonpolar. But there must be something different, and the only other difference we have to worry about is size. So one of these is physically larger than the other. Which one's going to be? Well, let's see. They're moving uphill against gravity, and gravity is going to affect the larger one the most. So the larger one will move slower. Does that make sense? And so this would be the large one, and this one would be the smaller one. So, understanding, those two principles, like dissolves in like, and polar amino acids tend to move farther in polar solvents, and nonpolar amino acids tend to move farther in nonpolar solvents because they have higher solubility. And in general, smaller molecules tend to move faster than larger molecules with similar properties. And those are probably, two things to, understand for this lab, as well as being able to calculate an unknown and from those numbers predict what that value is. So I think that wraps this one up, and good luck on it.